morning, everyone, and welcome to the second day of Zurich Hack. We're going to first have Tom's keynote. Tom is a member of he's been heavily involved with the Haskell.org Foundation. The Haskell.org committee, as well as the Haskell Foundation. He's currently working at Groq, which makes very fast chips for AI. I guess AI is a bit of a divisive subject, but there's some objective truth in like selling shovels during a gold rush, of course. Tom is also known in the Haskell world for doing Opaleye, which is a very cool and type-safe DSL for writing SQL queries. And more recently, he's been working on Bluefin, which is a really nice effect system library that gives you more sort of like first-class values for effect. I don't really know how much he's going to go into Bluefin today. It's more of like a generic talk about the history of effect system, which I think is quite interesting. So yeah, please take it away, Tom.
Effects. Effects are a very big topic in the Haskell ecosystem. We've got monads, we've got monad transformers, we've got effect systems. Some people swear by effect systems, some people hate effect systems. Put up your hand if you've used an effect system. This isn't a trick question. I'm not trying to debate what is the definition of an effect system, but it looks like about half the people here have used an effect system of some form or other. So if I jump back 2 years, now I'm back in 2023, my hand would be down. I have not used an effect system. How can this be? Because as Jasper just said, I developed the Bluefin effect system. Well, in 2023, what is Bluefin? I don't know what that is. I've hardly even touched an effect system myself. So how did I get from there to 2025, where I am a big fan of effect systems, particularly Bluefin? And how did Haskell get from its beginnings in the late 1980s to today, through a whole series of developments that led to where we are today in the world of effect systems and monads. That's what I'm going to talk about today. Not really much about Bluefin, because as of 2023, it doesn't even exist. So why does Haskell have this issue with effects anyway? What's that all about? The Haskell report was first published in about 1989, I think, late 80s, and it was defined to be a referentially transparent language. And referential transparency is a very technical property. I'm not going to try and define the technical property in this talk, because this isn't really a talk about any technical details. It's about vibes, it's about history, it's about intuition. But what I do want to say is that referential transparency is a very important aspect of what makes Haskell Haskell, but it also posed some challenges for the early implementers of Haskell. So if you want to print something to the screen and read something from the terminal, how can you do that in Haskell? What you want to do is a sequence of statements. You want to have a statement that says print something, and you want to have a statement that says read something. So put strlen and getLine in the Haskell world. But this is difficult in a referentially transparent setting, because referential transparency implies that you should be able to inline your let bindings without changing the meaning of your program. If I try to write some Haskell code like this doing effects, binding the result of effects to variables, well, I should also be able to, by referential transparency, inline those variables, in this case, the name variable, into getLine and into getLine. And then what does this program mean? When do the getLine actions actually run? This is very confusing. And this is before we even begin to think about laziness versus strictness, and so on and so forth. This just doesn't really work. This is not coherent. Same story for state. Many languages allow you to define a mutable reference cell, for example, that you can put in some initial value of state. In this case, it's just a string saying initial value. Pass the reference cell to a function along with some other arguments. The function will do something with that reference cell, modify it, put something new in it. And then after the function call is returned, you can get out the new value. in the reference cell and print it out. But again, this doesn't work in a referentially transparent setting. You can inline the definition of ref into the use of ref, and it looks like we're getting the ref of a completely new reference we're allocating with the same initial value, not the value after the call of f. So this is incoherent and doesn't work either. Same story for exception-like effects. In exception-like effects, you want to bracket regions of code with something like try, which says if an exception is thrown in this region of code, I want to be able to catch it and handle it. So here I'm throwing a string indicating that a value is too much, and I want to catch it in the try, handle it, and recover. But that's no good in a referentially transparent setting. If we can inline variable definitions, we can also do the opposite, take them out, might call it outlining. Here I've outlined this v function, v variable, that is the throw statement. And then when does the throw statement execute relative to the try block? Does it execute before the try block and we lose the exception? Does it execute within the try block nonetheless? Trying to assign any sort of reasonable, consistent behavior to this is very, very difficult. But there are some solutions. The ad hoc solution in this case is we use the either data type, which has two constructors, left and right, and we use left to indicate failure, and we use right to indicate success. And in that case, we're fine. We can just manually inspect the data constructor to see whether it's left or right. That indicates whether an exception was thrown or not. So this isn't an RTS exception. It's not something handled by the runtime system of the compiler of GHC. It's just some data in your program. We can also have an ad hoc solution for state. Rather than actually having a mutable reference cell, we're going to play a particular trick. We're going to pass in initial values of state, here S1, as an argument to the function f. And f is going to return the new modified value of state, S2, in its return tuple, along with its nominal return value, r. And then getting the final value of the state is just looking at S2. And this works fine as well. And for I/O, there's another approach that we can take. This one's called continuation passing style, and this was the way that you did I/O in Haskell, in the Haskell report, in around 1990. So instead of having a sequence of statements, one after the other, that perform I/O effects, you have a function putstrlen, which takes the string to print out, and then it takes as another argument the thing to do afterwards, which is the rest of the program. GetLine will get a line from the terminal, and its argument is what you do with that line. So we bind it to the variable called name, and then we do the rest of the program, so on and so forth. So this works fine as well, and it was how Haskell worked in about 1990. But these are all ad hoc solutions. Here's a general solution. It's called the monad, and the monad allows us to use the syntax called do notation. And I think monad was introduced into the Haskell world in about 1991 by Philip Wadler, although it came from the mathematical world, in the mathematics of programming language theory world. But this is such a nice solution to the problem that I don't think it really had to come from mathematics. I think it was just waiting to be discovered in Haskell all along. So we have the same sort of syntax to solve all of these problems. In the I/O case, we can write sequences of statements, we can bind the result of I/O actions to variables, and continue like that. In the state case, we define a data type which specifies how the state passing trick that I just described can be encoded as a monad. This data type reflects exactly the state passing trick, and the monad allows us to sequence actions like this that do the exact state passing that I showed on the previous slide under the hood. And exactly the same for the exception case. Here we have the definition of either with the left and right branches, and this allows us to sequence a sequence of statements that each of which can possibly throw this sort of exceptional value. So in these cases, state and either, we're defining data types that model computation. They describe how the computation should proceed. So that's all good, but the problem now is they're all just individual effects. What if I want to do IO and state and either all in the same function? Well, that's where monad transformers came in. This function does state and exceptions and IO all in the same function. The exact definition of the function is not terribly important, but it reads from the terminal, it gets the value of some integer state, does some comparison, and based on the comparison, it may or may not throw an exception. And we can do this because we've defined the accept T and state T monad transformers this time. They have the same structure as the either and state data type definitions that we saw on the previous slide, except now they can possibly happen in a further nested monad. In each case, they're called M here. And that's all well and good. It solves the problem, but it has a couple of problems of its own. Firstly, we have a fixed order of interpretation. So here I've very definitively put state T on the outside of this data definition, accept T inside one level, and IO at the bottom. And we also have to do a lot of manual lifting. We have to make sure that we lift the IO action 2 levels deep inside this stack of monad transformers in order to be able to perform the action. So that's quite a pain. The next thing was MTL, and I think this was introduced around 1994, 1995. This is a way of specifying the behavior of a block of code rather than by specifying a concrete monad transformer. We specify constraints on the monad to tell us exactly what that monad can do. So here, it's a monad that can do I/O, it can do state operations on an int, and it can throw error exceptions of type string. And it's exactly the same code here as before, except that no lifts. We do have a lift I/O here, actually. And depending on the definition of getLine, you don't even need that. But certainly the lifts for the state and the error are not there. So this is much simpler. We only have the lift I/O, and we have potentially variable order of interpretation, which means I don't have to worry that I wrote state T of accept T, and you wrote accept T of state T, and we don't know how to plug our code together. So this is much nicer. And what we get from this story is a very nice property of Haskell. We get these fine-grained effects. We can see exactly what our code can do in terms of effects. For example, let's say I didn't have the I/O in this type signature, because I/O is a very powerful effect. So if I just had monad state and monad error, I would know that I could only do state actions and error actions. Can't do any other types of effects. And this is a very nice property of Haskell. We're making invalid states unrepresentable. If we don't want to be able to do I/O, we just leave monad I/O off the type signature. And then the type checker will guarantee we're not going to do any I/O. But not everything is nice in the MTL world. The major issue of the MTL world is this O of n squared instances problem. And when you define an MTL effect, you define 2 things. You define a transformer that interprets that effect. So we've seen the state T and accept T transformer definitions on the previous slide. And you also define classes that allow us to plumb that effect around. And for every pair of transformer and class, you need an instance. And the instance tells you how the transformers and classes relate to each other. The ones down this diagonal, they tell you how the effect itself is implemented. And the ones off the diagonal, they tell you that you've got to ignore, for example, you've got to ignore state effects in exception and just pass them down the stack until you find an accept T that can handle them. So there's a lot of boilerplate in the off-diagonal elements here. But you do, one way or another, have to make sure that gets written and implemented. And that's because the MTL system is in a sort of open world system. There are no restrictions whatsoever on what effects you can define. Just anything that can be implemented as a monad transformer will work fine here. And there's some ergonomic issues as well. Can I have two different states in scope? I might want an integer state and a Boolean state and be able to operate on them independently. You can't do that. That just isn't allowed in MTL. There are technical reasons why that's the case, and so there are technical reasons why that's the case, which I'm not going to go into in more detail, but it's just a limitation imposed by MTL. You can get around that. If you want two states, you can just package your two states up into a tuple, a pair of states. If you want two reader environments, you can package them up into a tuple. Same with writer. Writer could also be an either of two possible written values, but because these are generally monoids, they're going to end up being equivalent. And for monad error, if you want to throw two different exception types, well, you can just package them up into one exception type, which is the either of both of them. But this is a bit of a pain. This is really quite manual and doesn't really feel like we should have to suffer through that. Now, meanwhile, while all this MTL stuff is going on, where we're writing monad transformers as data types in the Haskell language, there's another approach going on a different parallel thread. And that different approach is called ST. So to see how ST works, let's look at the example of state again and see three different approaches. The one we've already seen is the monad approach, where we define a state monad and we operate in the state monad. Here we're starting with 0 and we're adding in 1 to 10 and getting out 55. Now, in the IO monad, we do actually have the mutable reference cells that I talked about at the beginning, called IORefs. We can do the same thing in the IO monad, allocate an actual mutable reference cell in the GHC RTS, or indeed, as Lennart has just sat down to my left, the micro HS RTS. And we can add the numbers 1 to 10 into that reference cell and get out the final result, again, 55. So how do these differ? Well, I would say the bottom one is a lot nicer because it gets an integer out at the end, whereas the IO one, the int is trapped inside the IO. Once I've gone in the IO world, I can never get out. This int is always the same, but the type signature does not tell me that the integer is always the same. It's saying, oh, in theory, the integer could vary each time you run this IO action. So that's quite unsatisfactory. But here is a nice solution by John Launchbury and Simon Peyton-Jones from, I think, about 94 or 95. It's called the ST monad. We do exactly the same code as the IO code, except we use an ST-ref instead of an IO-ref. And underlying it is exactly the same data structure. It's also a mutable cell in the RTS. But we have this magical thing called runST with this magical-looking type called a rank2 type because it has for all s in it, nested inside here. And it allows the compiler to prove that every time you run this, it will give you the same result. It will give you the same int. And that way, you don't have to have any monad, no IO, no ST here. You've just got an int. And this is an extremely nice trick and based on some extremely powerful theory called relational parametricity, which I don't really understand at all, but it works incredibly well. And I call these two cases, state and ST, encapsulation, because you don't care about what's going on inside. You don't care that a mutable reference cell was used on the inside. All you care about is what it looks like from the outside. It's always an int, always the same int, so no need to have any IO or any monad wrapping this. And I contrast these two approaches by calling the state one a synthetic approach. You build up a state monad from smaller pieces, ADTs. Here it's products and functions. And I call this one analytic, because it really is using a very complicated piece of GHC RTS, or whatever Haskell compiler RTS you're using. But it's carving out a small piece, and it's saying this piece is well behaved. We know how this piece works, and we can guarantee some properties about this piece. So this is lovely, but the problem is that basically then nobody ever used it. If you only have state effects, that's extremely limiting in practice. So we have this really nice theory, really nice properties, but really underused, or really very little used compared to the monad transformers world.
I have a quick question.
Yes.
Can you just go back to the slide? What was the problem with example state? Why is example ST better than example state? I didn't.
Oh, is why this one better?
Yeah.
It's not better in terms of encapsulation. You get exactly the same properties. In terms of other properties, then I'll come on to that in a bit. Well, I'll give you a sneak preview of the answer. The answer is doing this kind of thing, particularly at scale, is very slow. That's the sneak preview, but we'll go into that in a lot more detail. So now let's take a little bit of a segue into a specific sort of effect. And this sort of effect is called non-determinism. Now, I don't think non-determinism is a particularly good name for this effect, because it's not really random or unpredictable in any way necessarily. It's more like you have the ability to branch computations and use computations in a way that isn't just from start to finish. You can proceed with your computation and you can go to the finish, but also go back to where you were and go to the finish again multiple times and sort of branch in your computation. Here's an example. If we have a tree and we want to calculate the sum of all sequences of numbers from root to leaf, well, this one going left gives me 1 plus 2, 3. This one going down here gives me 8, and this one going down all the way to the right is 9. Using a sort of non-determinism effect, in this case, it's the list monad. So this here is just the list type constructor. I can write this in a very straightforward way without having to manually manage the different sorts of state to keep around different numbers of state depending on how far I've already branched down this tree. So in the leaf case, I just add the final n, and that's the final result of my program. I get that and I return it. In the branch case, this is quite interesting. This is where the non-determinism comes into effect. I add the value of the particular node I'm at, and then this alternation operator here means I either go down tree 1 or I go down tree 2, and I calculate all the sums for that subtree. And somehow, this just works out to give you the correct answer. The plumbing of the state through the state monad works out so that no matter how many branches in this tree I could have branches for 100 levels going down, it will always make sure that the states calculating how the total sums so far are always kept separate from each other so that they never interfere. And this is one of the smallest examples you can have of this pattern, where you're essentially doing something like suspending computations and then resuming them later. So I suspend my computation at the 3 node, so I can proceed to either 4 or then resume later and proceed to 5. This is extremely powerful, but it's also extremely complicated. And as we're going to see, this effect ends up causing all sorts of problems for effect systems builders. And in the sort of MTL and synthetic world, you'll find them called, well, the list monad, logic T, list T done right, and ContT, which is the sort of biggest one of them all, which gives you the most power in this sort of non-deterministic or branching setting. So that is an example of the most complicated and challenging effect, and we're going to come back and see why that causes problems in a bit. So, from about 1995, where we had MTL and we had ST introduced. Oh, and by the way, the ST monad is called ST despite not being a transformer at all. If you see except T, state T, the T always means transformer, but when you see ST, it doesn't mean transformer at all. It means something completely different. In fact, I think it stands for state threads. But because it's hardly ever used, that doesn't really matter and no one ever gets confused. So we had these great things in 1995, and then there was really very little for about 20 years in terms of new technology for effects in Haskell. And in around 2015, it was the work of Oleg Kiselyov who really instigated a lot of new investigation into these things. He had a library called Extensible Effects, or maybe someone else, I'm not sure, wrote the library based on his work. There was an effects library by Sjoerd Visser, which came a bit before that, in fact. I think Sjoerd sort of anticipated this, but the real growth and excitement about extensible effects didn't happen until around 2015. And at the same time, Oleg Kiselyov was also promoting this notion of streaming, iterators, and so on for sequential computation. Now, streaming is actually an effect, but I'm not sure that was really understood. The link between these two sorts of things was really understood at that time. And I'll show you in a moment that, that MTL deals with these, extensible effects deals with the problems that MTL had by being essentially a closed world. Whereas MTL was an open world, and you could have any effects that you could possibly define as a monad transformer. That gave some issues regarding making them interact with each other. By definition, in extensible effects, you already know how they interact because they're in a closed world. But the closed world is basically the whole world. So we're putting delimiters around the whole world. Anything more or less that you can implement as a monad transformer, you can implement in extensible effects. And so we don't really lose anything by moving from monad transformers to extensible effects. So quick segue into streaming, because I really love streaming. I think it's a very powerful way of programming. They can also be called iterators, generators, enumerators, that sort of thing. And they were initially introduced, or when Oleg Kiselyov was introducing them, he promoted them as resource-safe, incremental, and declarative. Resource-safe really means that when you have finished using a resource, you should free it as soon as possible. Because for some reason, even in 2025, things like file handles, network sockets are still limited resources in operating systems. I don't understand why that is. I just program at the application level. But in the operating system level, apparently these things are still very scarce resources, and you don't want to lose leak file handles, leak network sockets, which means that you won't be able to open new ones when you need to. I think this is an extremely useful tool for separation of concerns in general, even when I'm not doing anything related to resource safety, file systems, anything like that. I think it's just extremely nice for separation of concerns in programming. You write one block of code that produces things and another block of code that consumes things, and they don't have to know anything about each other. And in 2025, the widely used streaming libraries that I'm aware of are these ones: Pipes, Conduit, Streaming, Streamly. And I'm now using Bluefin streams as my most used effect. I was really surprised by that. I thought it'd probably be state or exceptions. But when I'm programming in Bluefin, I use streams as my most used effect. So hopefully Bluefin will be added to that list as well as time goes on. So now, extensible effects. This is Polysemy code that I think is probably the most popular extensible effect library in Haskell at the moment. Polysemy came into existence in, I think, 2019, and it allows you to write essentially exactly the same code as we wrote for MTL. The type signature is slightly different. Instead of saying monad state int m, we say member state int r. And now r is a parameter to this sem monad. That's Polysemy's sem monad. This is why we have a closed world. Everything is closed within the sem world. And that's why we don't have to ever say anything about how these effects interact with each other. But other than that, this code is literally exactly the same. I think maybe we've got a throw instead of a throw error. So one of the names is different, but you don't have to lift. I think it's possible even... I think I actually got this wrong. I think this lift IO shouldn't be here. I think I've made a typo there. You don't have to lift IO either. But that may depend on exactly how the classes are set up. Actually, now I come to think of it, you probably need lift IO because member embed IO R gives you a monad IO instance for sem. Sorry? Yeah. The lift IO allows you to embed IO inside your sem. So yeah, the code is almost exactly the same. And you don't have an O(n) squared instances problem. That's nice. And you can have multiple effects of the same type. I can have an int state in scope and a string state in scope, no problem. Now, I can't have two int states in scope. So that's a bit of a pain, but okay, we live with that. I can't have two different classes that both, or two different constraints, both of which put in an int state into scope, unless they're the same constraint. So I'm stuck there a bit, but okay, we'll live with that, as long as we get other nice properties. The problem is these extensible effects are very slow. And this is Alexis King giving a talk 5 years ago at ZuriHack explaining why these extensible effects are very slow. And this is not what Alexis said. This is me putting words into her mouth because I call them synthetic effects. That's how I think of them, these effects that are built up from ADTs. That's not what Alexis said. But she explains why the effects built up from ADTs are always going to be slow. And there's not really anything you can do about that. Loads of great technical details in this talk, and I can't do it justice at all. So if you're interested in effect systems, I would definitely recommend this talk. But the long and short of it is, if you build up your effects like this from data types, in terms of performance, you're stuck. There's nothing you can do. She has an escape plan. It's got 4 sort of technical parts to it. And she explains this in her talk as well. I'm not going to... I'm not going to try to go into the technical details of it, but she has an escape plan, and she enacts her escape plan. That is her effect system called F, or EFF. And she gives another great talk at ZuriHack. Look, she's standing right here. And one of my hopes is that people will also like this talk, and in a couple of years' time, there'll be a slide of me standing here, showing the slide of Alexis, and we'll have another layer of recursion. And it'd be nice to see how far we can keep that recursion going. Haskell's a lazy language, so in theory we can go infinitely. You know, there's no reason we should ever stop. And the idea is that to implement all of these effects, which she calls algebraic effects, that's a sort of technical term as well, but it's essentially everything you can implement with ADTs in this monad transformer style. You can also implement using something called delimited continuations, which is another mind-bending programming language theory concept. And so she proposes to put delimited continuations inside GHC, so native primop support for delimited continuations, and then just do effects as the IO monad with some kind of stuff that tells you what effects are around. This IO monad can use the delimited continuations and do all the same effects that monad transformers can do, but in a much faster way, because we've just taken the GHC RTS and we've carved out bits of it, that behave in well-understood ways. That's what I call analytic. So again, not Alexis's words, but this is how I interpret her. When she's saying, let's put delimited continuation primop support in GHC, she's saying, let's use analytic continuations, not synthetic ones like ContT. Let's use analytic ones that are built in, and let's carve that up using the type system so we always use it in good ways. And unfortunately, that just did not work. And Alexis has a third great talk. This time it was a talk on her Twitch channel. It's called The Unresolved Challenges of Scope Effects. And there were type system holes in this approach. You can either put in some dynamic checks to make sure that you're using these delimited continuations in the right way, in which case it's a bit slow, probably not as slow as MTL, but it's a bit sad in Haskell where we have a type system to use dynamic checks all the time. Or you don't put the dynamic checks in, and it ends up you can cause seg faults in your Haskell program. This is very, very sad, and this is what Alexis had to say about it. If you just rule out effects that require delimited continuations, you throw out coroutines, I'll come back to that, you throw out non-determinism, then you don't run into these issues, because you can't do this thing where you suspend the computation and resume it later. So what I was saying before about logic T causing problems for effect system implementers, this is exactly what happens. If you're using these delimited continuations in the GHC RTS, then it's really hard to define a type system that means that you can't use them incorrectly and avoid seg faults. And for very similar reasons, not actually the same reasons, because Polysemy doesn't use these, but also related to what's called non-determinism. This is Sandy Maguire, who developed Polysemy. When a similar bug was reported to him, he ended up saying, "I hate programming." These delimited continuations have been a huge pain for effect system implementers. So what can we do about Alexis's escape plan? She wanted to handle all algebraic effects. Logic T, ContT, non-determinism. That meant you needed delimited continuations. Well, let's take a completely different approach. This was Michael Snoiman's idea. And I think this was even before, actually, this was probably before 2020. Michael Snoiman had been saying, resource safety is an extremely critical problem. That's what I mentioned before. Make sure you free resources not too late after you've stopped using them. Here's how we do it in the case of files with I/O in Haskell. We have a with_file function. And the with_file function takes care to bracket the body of the computation. That means that we open the file, we get the file handle, and we run the body with the file handle. But if any exception is thrown within the body, the bracket makes sure that it closes the file and releases the file handle before it propagates the exception on further. And this is the kind of thing you really need in order to have resource safety in Haskell. And this reader TIO pattern works really well. You have a reader T, which just basically means it bundles up a bunch of stuff for you to pass throughout your program. So you have access to database connections, application state, and so on. But other than that, for effects, you just use I/O. You don't use anything complicated like effect systems. You don't even use monad transformers or MTL. You just use I/O for all your effects. You can throw exceptions. You can use mutable state refs, IORefs. But you don't get any encapsulation. This is very sad. It means that anytime you need to do an effect, you've always got I/O, regardless of whether that effect is visible outside of what you've written. So unlike the ST case, where ST could prove that the state effect was not visible outside, in the I/O world, you can't do that. So that's very sad. Reader TIO works, it's practical, it's very widely used in the Haskell world, but I just found it very disappointing. So here I am in 2023 thinking, I'm just disappointed by effect systems. They're not really giving me what I want, and I don't see any particular good solution. And then something fantastic happened. This is Andrzej Rubczak, He invented the effectful type system, and he worked out how to hit all of Alexis's requirements apart from the one to handle all algebraic effects. So Alexis was going to wrap up I/O in a new type and use delimited continuations. And Andrzej said, well, why don't we do that? Wrap up I/O in a new type, but don't even use the delimited continuations. Those were the things that were really hard. Those were the things that caused seg faults, type safety violations. So he's using an analytic effect, carving up I/O into well-defined pieces, but not doing everything. No non-determinism, no logic T equivalent, but if you want them, you've still got logic T, you've still got ContT, and you can wrap them around effectful's F monad. And here the code is exactly the same as the Polysemy code. The name of throw error always varies for one reason or another, but get and put are always the same regardless of the effect system. So this is exactly the same, except we have a slightly different constraint that means, again, essentially the same thing. And it does what the Polysemy code did, but it's not built out of these synthetic effects. It's not representing effects as data, so it's much, much better performing. And I think this is going to be one of the key observations in the history of Haskell, that we can unify these two separate pieces. We can unify the encapsulation world, where we really want to be able to indicate that from the outside, values calculated using effects do not actually have that affecting behavior. The affecting behavior is only on the inside, whilst at the same time being high performance. So this is a little table of what we get in different worlds. In the I/O and reader I/O world, we don't get the encapsulation, we don't get the fine-grained effects. We're either in I/O or we're not, and when we're in I/O, we're stuck. But we do get resource safety, and we do get predictable performance. Oh, and we don't get non-determinism per se, but we can get it back through using ContT if we want. In the synthetic ADT world, which is the effect system world, the MTL world, the transformers world, polysemy, fused effects, and so on, we do get the encapsulation, we do get the fine-grained effects, but we don't get the resource safety or the predictable performance. And we kind of get non-determinism, but as Sandy Maguire demonstrated on that issue, it can go wrong. You know, it still doesn't seem watertight. In Alexis's world, we do get all the nice things. I'm not 100% sure about what Alexis's story in F was going to be around resource safety, but in principle, that could possibly work. But non-determinism doesn't work. That led to seg faults. And in Andrzej's world, we do have all these nice things. We get encapsulation and fine-grained effects, and at the same time, we get resource safety and we get predictable performance. And what we give up is this thing called non-determinism. That's the branching computation. That's the delimited continuation thing. Most Haskellers are not using non-determinism, and generally when they need it, it's more or less okay to reach for a ContT monad or a logic T monad transformer and just do it that way. So Andrzej's world gives you 99% of what you want, and it gives up just this 1% that you probably weren't using very much anyway. So for most programmers and for most programs, this works fantastically. Then I came along about a year or two later, and I developed a library called Bluefin, which is extremely inspired by Effectful. I don't think it would have existed if Effectful didn't exist. And it's different in basically only one way. So Effectful carries around this environment in its new type and does all its effects in I/O. Bluefin does not even carry around an environment. So where do the effects come from? Well, in the Effectful world, the presence of effects was marked by constraints. And in the Bluefin world, the presence of effects is marked by arguments. These are value-level arguments. I pass in a handle to an exception or a capability to throw an exception. It's a value-level thing in my program. It's bound to a variable name. I pass it around. Same for state. This is very much like an IORef or an STRef that we saw before. It's a mutable cell, literally. It corresponds to a mutable cell in the runtime system that you can update the value of. And you pass these things around. In both cases, you get encapsulation. Here I am removing the error effect from scope by handling it with the function called runErrorNoCallStack. It handles the error effect. It converts it to an either, and then we decide what to do. And in the Bluefin world, the equivalent called try, it brings the exception capability into scope. You bind it here in this lambda. Then you can pass it into a function that needs the ability to throw exceptions. And when you've handled it, it doesn't appear in the type signature anymore. So this is encapsulation as well. So effectful is a little bit complicated in a way. There's something going on in this env. What is it? I don't really know. But Bluefin is really simple. It's as simple as possible and no simpler. It's not really doing anything. It's just wrapping up I/O, chopping it into bits, and saying these different bits have well-defined behaviors that interact with each other in a well-defined way. And one way of looking at this is the well-scoped handle pattern. Our very own Jasper here wrote one of the seminal articles about the handle pattern over 10 years ago, I think, describing how to pass around values in your Haskell program that allow you access to different resources. And Bluefin's doing that in a well-scoped way. Everything is tracked, so you can make sure that effects don't happen where you don't want them to. And in this way, Bluefin is the spiritual successor to ST. In theory, it could have been, ST could have been this 30 years ago. But the ability to carve these things up in a fine-grained way to give you state, to give you exceptions, to give you streams, to give you well-scoped jumps, just wasn't appreciated in those days. There's a couple of hands up. One here, I think, was the first. The question is EX here just a throw function? So basically, yes. It's actually a throw function in a new type, because if you have the actual throw function here, it becomes a little bit hard to type. It has a rank 2 type itself. But yes, that's exactly the right intuition. It just passes you the function that allows you to throw.
With the monad transformer stacks, you said that one of the sad things was interpretation order. With this, don't you kind of now have all these functions where you have to interpret them in the same order, and now you're going to like switch arguments around, and you have to kind of like juggle all these arguments?
So yes, I mean, if I wanted to interpret state on the outside and exception on the inside, I'd have to have a higher level run state block here that brings a state into scope, well, ST, and here the try block brings EX into scope. And if I wanted to interpret them the other way, then I'd have to reorder them so that the run state was nested inside the try. But that's not really any different from doing it in any of these other systems. It really is just taking a try out and putting it at a higher level. And you have to bring the EX with it, because that's what it produces. But it's just chopping those bits out and moving them to a higher level. Yes?
What constraints go on the dots there?
So the question is, what constraints go in the dots here? So the constraint is that this effect E1 belongs to E's, and this E2 belongs to E's. And here, the constraint would just be that this E1 belongs to E's. So this is the way that we keep track and make sure that the effects that you see can only be used in a well-scoped way.
So negative constraints are always gnarly. So when you want to eventually fully get out of the effect world, how hard or how ugly it is to ensure that you're not using I/O internally? Because I imagine at some point you want to give a function that goes from F A to A, if only I/O is not really used, and then you use unsafe perform I/O. Like that's the ultimate encapsulation, right?
Yeah, that's right. So yeah, I haven't got an example here, but in both cases, Effectful and Bluefin, the point is that if you don't have any I/O effect in scope, you can just run it to a pure value. So if you have in the Effectful world, well, in fact, it's exactly the same in both worlds. For all e's, f, e's, r, you can run that just to get a pure value r that doesn't have any effects in scope. And in that way, it's basically the same as what ST was doing. I've got a couple more slides, so I'll just press on before taking any more questions, but it's only one or two. So hold on for a couple of minutes, and then I'll get to all your questions. So one question I get a lot, actually, is, isn't this just a pain passing around stuff? Didn't we invent monads so we don't have to pass around stuff? And I think that's a fair question, very understandable. But in practice, I have not found this a pain at all. Quite the opposite. I found it extremely liberating, having a value that I can pass around and know which effects I have in scope where, and not have to worry about whether effects are being passed around implicitly or not at the type level as constraints. So this is really extremely effective, and it's particularly effective when I use streams, because you can connect streams and consumers together by taking kind of values that represent their ends and sort of plugging them together. So this is actually extremely ergonomic, at least in my experience. So I just want to say something about the future. This was mostly about the past 35 years or more. But what might the future hold for effect systems? Well, one question is, can a different use of the type system make delimited continuation safe? And can we go back to Alexis's project? And maybe we can. One thing happening along those lines is this thing called heftier effects, which is a new effect system that's come out in the last year. It's a synthetic system, so it's going to be slow, but the author claims that the type system is actually solid with regard to these delimited continuation issues. And if that's so, maybe we could use the same type system and wrap it around an analytic system like Alexis's F and get a type-safe way of using delimited continuations. Another possible approach is called Bluefin algae. This is not mine, but it's by Li Yao Xia. It's a Bluefin style type system, but over delimited continuations. So perhaps this is the type system that's needed to allow, to prevent the kind of issues we saw in F, where these continuations can kind of escape their scope and be used in the wrong place and lead to runtime errors or seg faults. I don't really know. I have not looked into this in any more detail, but if I was going to start looking, those are the two places that I'd start looking. So there could be hope for delimited continuations. And another big question is, don't all these effect systems fork the ecosystem? We had freer effects, fused effects, polysemy, extensible effects, Effectful, Bluefin. Am I just not forking the ecosystem further? Well, I'm less concerned about that in the realm of analytic effects, because underneath they're all I/O. So ultimately, they should be interconvertible. And there are some issues to do with how they use the type system. Can we ensure that they can be interconverted safely with regard to their respective type system? I don't know. There's a lot of work to do on that. But at least in principle, I/O wrapper or analytic effect systems, as I call them, could be interconvertible. So we've got to put in the work to do that, but I'm less concerned about forking in that case. And finally, before proceeding to any questions, I work for a firm called Groq. We're writing a state-of-the-art AI compiler in Haskell, amongst other languages. We're always hiring. It's great fun. I've been doing a lot of fun Haskell and a lot of fun Bluefin at Groq. And if you're at all interested in that, then please check out our careers page. You can come and talk to me about anything to do with Groq or Bluefin or effects or Haskell in general. I'd be very happy to come to hear from you. So thanks very much. Thanks for listening. That's all from my talk. And I'd love to take your questions.
Thank you, great talk. One question, have you looked into the capability library at all? Disclaimer, I wrote much of it, but...
Okay, with Arno as well.
Yes.
Yes. I've had some correspondence with Arno about that. Yeah, so this is quite a similar idea. The notion of capabilities as values that you pass around that allow you to do things and whose absence prevents you from doing things is very similar to what Bluefin's doing. In Bluefin, I normally call them handles, but you could also call them capabilities. So I have had a look at capability a bit, and I can't remember. I should have added it to the list there, actually, so I apologize for that. I can't remember if I guess it's a synthetic system. You're building things up from...
Well, it's sort of MTL style in the sense that it's all type classes, but it gets away with the boilerplate by using deriving via. It's sort of a type system, EDSL, to construct deriving via paths.
Yeah.
And I mean, regarding your last slide, it makes me wonder whether it could perhaps be a way to, have a unified interface over multiple effect systems. I don't know if that's possible. I would have to think more about that, but maybe that would be something to look into.
So the MTL style classes can still be used with these analytic systems. And in fact, you can give instances, but once you're sort of in that world, it's harder to get out. Even that, I think, is possible. But yeah, the ergonomics of making these different parts of the Haskell world play well together with each other, that still requires a bunch of work. Yeah, thanks.
Over here. So I have one. If you have like a lot of arguments, you can probably bundle them with has field again. So you get like a list of has fields. So you get like the list of constraints again. And I'm really hoping that Haskell base is gonna get like labeled anonymous tuples, because labels are actually useful now, and I've used them to great effect. So a question is. So I have two questions. So for the conduit-like effects streaming thing, do you like use the same thing as conduit, where you have like an ADT and then you try to fuse different effects together, or do you have like how do you call them, like a more straightforward or like in IO system of doing it that is more performant? And the other question is. So for ST, you have this for all S, which basically ties the knot, right? So if you run ST, then the S gets eliminated and you get the result back. But like for your system, you have to have, every function has to say, oh, these effects correspond to this ES. And then do you have to somehow like do the for all E or something for, if you say like try, and you get the exception, does the try contain like some for all, some rank N for all? In its signature somewhere?
Yeah, it does.
Oh, okay. So
that's how we deal with that problem. The previous question about streams. The remarkable thing to me was that I didn't implement Bluefin thinking it would handle streams. I thought it would handle I/O, state, exceptions, and then I realized if you want streams, you can just use a function. So the stream implementation of Haskell, in fact, what's called the coroutine implementation, is just a function. A coroutine that receives A's and returns B's is just a function from A to IOB, basically, under the hood. And there was this idea floating around that you can't do coroutines in this analytic setup. In fact, Effectful's README still says that you can't do it, but you can. Maybe they're not quite full coroutines in this non-determinism setting that people really want, but you can do essentially everything you want. And I've re-implemented the entirety of the pipes prelude in Bluefin, and it's just a function call, which was astonishing to me. And about your initial comment, yeah, you can just tuple up effects into product types, basically, into tuples. It's slightly more complicated because you have an effect tag that you have to make sure that you match the effect tag. But it really is just programming like any programming in Haskell, passing values to functions. If you always pass these three values around together, you may as well bundle them up into a product type and pass them together.
Hi, Tom. Thanks for the talk. How do you think about granularity of effects, in particular you spoke about ecosystem existence and these different analytic libraries all working together. If they're all using the same effects, then great. But if it's different, how do you then think about that?
Well, ultimately, the effects are going to be implemented in an analytic setting where you're just wrapping IO wrapper effect systems. The effects are all ultimately going to be implemented in terms of state, exceptions, and general IO, and just function calls based on those things. So ultimately, they'll boil down to the same stuff. So it's not like the effect system world where you can define your own effects out of arbitrarily small pieces. So I think the compatibility problem doesn't extend in the same way, because you just have to look at how state corresponds to state, exceptions correspond to exceptions, and just running arbitrary IO is always just going to be running arbitrary IO.
When using transformers, you get different behavior if you put state T over except T or except T over state T. It determines whether the state is going to roll back when you catch an exception. So which of the behaviors do we get with the effect systems, and what if we want the other one?
So I think the rollback issue is overstated. You basically just lose your state in the case of an exception if you put if you handle except T at a higher level. The state there is no space for the state in the type. The situation in which you get rollback is when you have things like logic T as well, and the logic T somehow miraculously ensures when it's plugged into state T that that you get this sort of backtracking behavior, and you can use your previous value of state for the next branch, for the next continuation. But in terms of what actually happens in Bluefin, you get the same behavior as you would if you had a concrete stack of transformers. If you have except T of state T of whatever, then it's exactly the same as handling except T in Bluefin at the inner level and handling state T at the higher level. And the same if you switch those. So you get exactly the same behavior.
You mentioned in your talk that there are lots of effect libraries, and it can be a bit difficult to choose one. I think in OCaml a few years ago, the effects and handlers were put into the language so that you have native support for that. Do you think this could be a way going forward for Haskell to sort of combine the effects, the effort into effects and handlers for the language?
Possibly. I don't really know much about that. And the compiler support necessary for that, or well, the runtime support necessary for that, was the work Alexis did on delimited continuations. So that's what you need operationally to get these things to work out. How you expose that to the user in a safe way is a different question. And I don't know how OCaml does it and how they avoid the seg faults that Alexis found when using F. Maybe they do have these dynamic checks to make sure that you can't run continuations in the wrong scope. I'm not sure. Or maybe they give up something else that means that you're a bit more limited in how you can use them. But if we can find a fully general way that is also safe, then yeah, why not? Why not implement them sort of by default in the lowest levels of GHC or base? Yeah, it could just be the new IO monad, the sort of algebraic effects, extensible effects monad, if it's fully general, and then anything else could be done on top of that.
Hey, Tom, possibly kind of a naive question, but for these systems that are sort of based on IO, in the cases where you don't need it, could you base them on ST, and would there be any benefit to that?
Well, ST really is just IO with a different skin and a limited set of operations. So ultimately, they're all doing the same thing. I think it'd be technically quite hard to even do that and sort of determine when you need IO and when you need ST. So I'm not sure there's much practical purpose of that. But really, they are the same thing. So you may as well just do them the same.
Just one final question. So in the MTL world, the accept effect that you have corresponds to the ability to both try and catch exceptions. And in Bluefin, it seems like the effect is to throw and catch is the handler.
Yeah.
And the MTL approach sort of gives you more complicated interaction with the state that was previously discussed.
Yeah, that's right. And I don't really understand this. Maybe that is the issue about transactional state. I don't know, but I have never come across a case where I wanted that. So I just don't have it. I mean, in principle, Bluefin has the ability to update handlers at runtime. So you could have a dynamically defined handler like you would have a dynamically defined catch in MTL. But I don't get why people need that. Maybe it's because it allows you to mix it with logic T and non-determinism. I'm not sure. But I've never gone into that world. So I just implemented the most simple thing I could, and it solved all my use cases so far. But yeah, that's as yet unexplained.
Let's thank the speaker again.
Do it like this.
Okay, yeah, that was a great... Actually, do you want to do the podcast thing first? It's not in the schedule, right?
Yeah.
Okay.
Good. A little announcement, something that's not on the schedule yet. So currently, we just thought we'd do it as a sort of a side event since the schedule was anyway looked a bit too cramped. So now we can cramp it up in your heads instead of on the schedule. So Pedro, who's there, and me thought it would be a good idea to have a podcast episode for the Haskell interlude and the Type Theory for All interlude recorded at ZuriHack at some time when the Aula is not being used by something else. So we're planning to do that now in maybe about 10 minutes or so. Yeah, so we're going to have a live podcast episode recorded here. And yeah, in case you're interested in being part of this, please stay here or have a toilet break and come back. And then we'll, maybe in about 10 minutes or so, when we get everything set up, we'll start that. It should go on for 1 or 2 hours. We don't know. We're just trying something out. Yeah, good. How many of you will like to be there? Hands up. Oh yeah, cool. So yeah, so maybe come around this area. We have enough space then, and we'll do that. Great. And
yeah. Then
wait.
After the podcast episode, and I think very soon already, in like 15 minutes, we'll have the food trucks starting to serve. So again, like yesterday, it is useful to sort of spread out throughout the lunchtime so that the queues don't get too long. In the afternoon, we have the second part of the beginner's track by Andres, and we have the category theory track as well. The category theory track will take place here.
That is true. Yeah, Richard is there. Yeah. One thing I forgot to mention, the podcast episode will be with Leonard Augustin. Yeah, maybe like, just forgot to mention that. So, yeah.
And then after the category tier track, we have a talk about taking risk at Mercury by Alex Vieth, followed again by food in the evening. And then, of course, we invite you to hang out and hack during the day and in the evening. One more thing, we still have T-shirts. So if you want the second T-shirt or you didn't get one yesterday, feel free to come by the reception and pick one up. On the same note, we are still selling some hoodies. If you want to support ZuriHack, you can buy a hoodie for us for 55 francs. Yeah, okay. Thank you.
Thank you. Cool.
when the